Hello, everybody. Hope you guys all had a nice weekend. We're back here on Monday to talk about the E2 reaction. So our goals for today are to hopefully finish up chapter 9. So the last mechanism we have to discuss is the E2 elimination. So we'll talk about the E2 in terms of mechanism, regiochem, stereochem. And once we wrap up the E2 reaction, we'll be ready to ultimately come up with some criteria to decide whether a reaction would be predicted to undergo an SN1, SN2, E1, or E2 mechanism given a set of criteria. Okay, so let's jump into the E2 reaction. So remember that E in E2 stands for elimination, so we still expect to eliminate a leaving group to form a pi bond. But we can see that, based on the 2, we've learned that that means for these mechanisms that this will be a bimolecular in terms of the rate. So remember that the E1 mechanism we covered on Friday went through a carbocation intermediate, and it was unimolecular in that it only, the reaction rate only depended on the concentration of the starting material, the alkyl halide. So we're definitely going to see a different mechanism with the E2 reaction because we've changed the rate expression, meaning we've changed the rate determining step. So let's go ahead and start looking at this reaction. Okay, so we're going to take this halide and we're going to treat it with a strong base. And we oftentimes are going to have the solvent be the conjugate acid of the base that we're using. So in this case, water is our solvent. Okay, and when we do an elimination, remember that we eliminate our leaving group and we generate an alkene. Okay, so I just want to look at this quickly because if you look at this tertiary bromide, okay, so when we looked at the SN1 and E1 mechanisms, this was our starting material. We used the same tertiary bromide to undergo those reactions. Okay, so one thing we should note right off the bat is that it seems like tertiary halides are going to be suitable starting materials for the E2 reaction. Okay, and then, how is this different than the SN1E1 that we learned on Friday? Well, notice that we have this strong base, strong nucleophile. Okay, in the context of this reaction, we only care about it being a strong base, but sodium hydroxide would also be a strong nucleophile. Okay, so one of the determining factors between the 1 mechanisms, SN1 and E1, and then the 2's mechanism, SN2 and E2, is the strength of the base or nucleophile. So strong bases, strong nucleophiles favor the 2's reaction, SN2 and E2. And we'll delineate all this once we're done talking about E2, but I wanted to start pointing out some of these differences as we go along. Okay, so in terms of the product, we actually can't tell the difference between the E1 elimination product and the E2 elimination product because they're the same, right? But mechanistically, they are different. Okay, so let me just draw the mechanism and then I'm gonna say a few things about the mechanism. Okay. So here was our starting material. So this is a bimolecular in the rate expression. Okay, and so remember when we were looking at dehydrohalogenation to form alkynes in chapter 7, that was an E2 reaction. So remember that we eliminated the hydrogen, or we, deprotonated that hydrogen and then eliminated the leaving group all at the same time. Okay, so the role of the base here is going to be to take that proton at the adjacent carbon. We're going to donate those electrons to make the pi bond, and the leaving group is going to leave. So it's a single step concerted mechanism. Let me draw that a little bit more clearly. So a single step concerted mechanism. Single step concerted mechanism. Okay, and that's where we're going to arrive at the bimolecular rate expression. There's 2 molecules in the rate determining step. There's only 1 step, so it is the rate determining step. So the rate expression then is going to be our rate constant times the concentration of our electrophile times the concentration of our base. In this case, it's hydroxide. So we can see that it's bimolecular in terms of the rate. So the rate expression for the E2 reaction and the SN2 reaction are more or less the same, right? But we'll have different alkyl halides that can undergo E2 versus SN2 as one of our main criteria. Okay, so there's a nomenclature thing or a classification thing that I need to tell you about before we move on. So let me redraw that same starting material. So we actually have a way to more specifically refer to the positions of our molecule that's undergoing the E2 reaction. Okay, so we use the Greek alphabet to help us indicate the position of various carbons within the molecule. So the carbon that bears the leaving group, we call this the alpha carbon. Okay, so the alpha carbon bears the leaving group. Okay, and any carbon that is attached to the alpha carbon is called the beta carbon. Okay, so we have 3 beta carbons. Okay, so a beta carbon is attached to the alpha carbon. Okay, and then any hydrogen that's attached to a beta carbon is a beta hydrogen. So a beta hydrogen is attached to a beta carbon. Okay, so these would all be beta hydrogens. Okay, and the reason why this is important is because in the mechanism, this is an example of a beta hydride elimination. Okay, so we're taking the hydrogen from the beta position, so a beta hydrogen elimination. Okay, so the other reason why it's important is because we're going to talk about a requirement between the beta hydrogen and the leaving group in terms of stereochemistry. So I need you guys all to realize what I'm referring to when I say the beta hydrogen. Okay, so the beta hydrogen is one of the hydrogens at the beta position. It's one of the hydrogens that we can remove to do the elimination. Okay, so we'll revisit this term beta hydrogen a lot throughout the rest of the lecture today as I refer to the hydrogens that are participating in this mechanism. Okay, so just to reiterate one last time, the alpha carbon is the carbon that bears the leaving group. Okay, and then any carbon that's attached to the alpha position is the beta. Okay, and then the hydrogens are classified based on the carbon they're attached to. So the hydrogens attached to the beta carbon will be beta hydrogens, and we are going to remove one of those beta hydrogens in our E2 elimination. Okay, so we'll see how that terminology fits in with our discussion as we move throughout lecture today. All right, so the first thing, we basically have 3 issues we need to talk about beyond the mechanism, and that is the regiochemistry or the regioselectivity of this reaction. We also need to talk about the stereospecificity of this reaction. So unlike the E1 mechanism, the E2 mechanism is stereospecific. Okay, so we'll see how that fits in with an elimination here in a little bit. And then we also need to talk about the rate dependence on the alkyl halide. Like, is a primary, secondary, or tertiary a better alkyl halide for the E2 elimination? Okay, so we're going to start with the regiochemistry. So remember, as it relates to eliminations, the regiochemistry really is asking where do we form the double bond? Do we form it at the more substituted Zaitsev side or the less substituted Hofmann side? Okay, so let's go ahead and look at this as an example starting material. Okay, so we're going to do this reaction with sodium methoxide. Okay, and often in E2 conditions, we'll see, again, the conjugate acid of our base utilized as the solvent. So if sodium methoxide is our base, then methanol would be our solvent. Okay, and so let's use our alpha beta terminology. Okay, so alpha is the carbon that bears the leaving group, and then we have the beta positions that are attached to alpha. Okay, so we could notice here that whether I remove the beta hydrogen at beta 1, okay, so I'll draw that in, or one of the hydrogens at beta 2, I'll rewrite that beta 2, but let me draw the hydrogens in. Okay, so whether I remove the hydrogen at the beta 1 carbon or at the beta 2 carbon, I would get a different product. Sorry, I'm going to relabel that one more time. Okay, so let's draw what those 2 products would be, and then we'll think about the mechanism and which one might dominate. Okay, so if I remove the hydrogen from the beta 1 carbon, I would get to that alkene. Okay, or I could potentially remove one of the hydrogens at what I labeled the beta 2 carbon, and I would get to that alkene. Okay, so we learned the terminology for these products. So we learned that the more substitutive alkene is called the Zaitsev product. It's the more stable alkene. We learned that the less substituted alkene was called the Hofmann product. Okay, so when we use methoxide as a base, we arrive at the Zaitsev product as the major product and the Hofmann product as the minor product. So that is, basically what we saw for the E1 elimination. Okay, one thing I will note as we're looking at this is between SN2 and E2, there will typically be a clear winner. So we'll talk about what those criteria are, but in this case, E2 would be the major product. And we wouldn't also have to include the SN2 product. And I'll discuss more about that when we're done talking about the E2 reaction in all of its details. Okay, so I want to present to you a different scenario. Okay, and so maybe we should draw the mechanism to get to that product that we showed there as the major product. So there's the hydrogen that I'm going to remove. We had methoxide as our base. Okay, so here is the mechanism to get to the major product shown. Okay, so that gave us the major product. All right, so I want to present to you another scenario. So I'm going to use the same starting material, but now I'm going to change the identity of the base. Okay, so we have this potassium tert-butoxide and T-butanol. Okay, so what do you remember about potassium tert-butoxide? So let me remind you where we talked about this previously. Okay, so when we were talking about nucleophilicity under the SN2 reaction, we talked about this type of base that was non-nucleophilic. We called them bulky bases. Okay, so remember that potassium tert-butoxide is one of our bulky bases. Okay, it's a non-nucleophilic base. It's also a sterically hindered base. Okay, so let me draw, we would have the same two potential products. Okay, and we would still call them Zaitsev and Hofmann. Okay, so Zaitsev means more substituted, Hofmann means less substituted. But notice, we actually alter the regioselectivity. Now, the Hofmann product is the major product. So the identity of the base actually influences what the major product is. So another way to say that is we could alter the regioselectivity by changing the base. Okay, so let's try to rationalize why there is a regioselectivity difference between methoxide and tert-butoxide. Okay, so let's think about that bulky base, potassium tert-butoxide. Okay, it's a bulky base, right? So its ability to access a beta hydrogen is limited, right? So the speed at which it can approach a certain beta hydrogen is dependent on the steric environment of that beta hydrogen. Okay, so if we were to draw, our starting material again and fill in those two hydrogens that we had referred to at the two beta positions. Okay, so here's our two potential beta hydrogens. We have those primary beta hydrogens on the right, and then that tertiary beta hydrogen on the left. Which one of those set of beta hydrogens would be more accessible by our sterically hindered base? Right, it would be the primary beta hydrogens. Okay, so these primary beta hydrogens are more accessible by the bulky base. Okay, so it's easier for the bulky base, being a sterically hindered base, to approach that primary position rather than trying to, fit its way in between these two methyl groups to remove that tertiary beta hydrogen. Okay, so bulky bases are going to remove the most sterically accessible beta hydrogen, and that leads to a shift in the regiochemistry so that the Hofmann product would be our major product. Okay, so let's just make that note that that I just said in words. Okay, so bulky bases alter the regioselectivity. Okay, so we saw that they react with the most accessible beta hydrogen. And that leads us to the Hofmann product. Okay, so the last thing that I want to mention here is, well, what were our bulky bases? So for our purposes, the bulky bases are tert-butoxide. Okay, so one way we could abbreviate that is T-bu-OK, right? But that is the abbreviation for the T-butyl group, and then our oxygen anion, potassium cation. So its structure is the one we just had up there. Okay, and then the other one was LDA, and LDA was lithium diisopropylamide. Okay, so those are our two bulky bases. Let me make sure that's clear that that is a T. Okay, and so those two bulky bases are the ones that we'll use for our purposes. There are other examples of bulky bases. We just aren't gonna, see them for our purposes. But if you are trying to predict the E2 product using a bulky base, a non-nucleophilic sterically hindered base, you will arrive at the Hofmann product as your major product. Okay, and so when we use non-bulky bases, like we did in the case of methoxide in our first example, our regiochemistry would follow Zaitsev's rule and we would get the most substituted alkene as the major product. Okay, so just to recap that in one sentence then, the base that we're using in the E2 reaction is going to determine the regioselectivity. Okay, so in some cases we'll get the Zaitsev as the major product, other cases we'll get the Hofmann product as the major product. All right, so the next thing that I want to talk about for the E2 reaction is the relationship between the electrophile and the rate. So is a primary, secondary, or tertiary halide fastest under these reactions? Okay, so let's talk about the structure of the electrophile. All right, so let's write out the same series that we wrote for all of our other reactions. So we have the methyl, we have primary, we have secondary, and then we have our tertiary halides. All right, so methyl, primary, secondary, tertiary. So first, let's look at the methyl halide. What's the deal with a methyl halide? Can it even undergo elimination? So you should ask yourself, is there a beta hydrogen that I could remove? No, right? There's only the alpha carbon and the alpha hydrogen. So the methyl cannot undergo E2. And we'll just make a note, no beta hydrogen or beta carbon. Okay, and then from there, the rate dependence is actually, as we increase substitution, we have an increasing rate of E2. So increasing rate of E2. Okay, so I want you to think about this for a second and think about the other rate relationships that we've seen for SN1E1, for SN2, and now for E2. Only one of them is different than the other three. Okay, so SN1E1 and E2 all prefer a more substituted electrophile. SN2 is the only one that prefers an unhindered electrophile. Okay, so SN2 is the one that prefers methyl and primary. All the rest of them, SN1E1 and E2, all prefer a more substituted electrophile. Okay, so why might it be in the E2 reaction that I prefer a tertiary halide over secondary over primary? So there's a couple of factors that control this rate, and so I'll just list them. Okay, so factors controlling this rate relationship. Factors controlling the rate relationship. Okay, so remember that we're kind of thinking, in the most ideal situations, we'd have an SN2 reaction, and anything that hinders the SN2 reaction is going to promote either SN1E1, and now we're learning it could also promote E2. So one of them is the competition with E2. So, both the SN2 and E2 require a strong base-strong nucleophile, okay? But if an SN2 cannot operate, like in the case of a tertiary halide, then what's left to happen? Well, it would be an E2 elimination. Okay, so as we decrease the rate of SN2 by increasing the substitution at our electrophile, we artificially increase the rate of E2. Okay, the other thing is a statistical argument, and that is just having to do with the number of beta hydrogens. So as I increase the substitution at my alpha carbon, I increase the number of potential beta hydrogens. Okay, so it would be, more likely that our base, or more likely that our base would run into one of these beta hydrogens. And then the last thing is the stability of the transition state, which is determined by the stability of the alkene. Okay, so we'll just make a note here. So the stability of the products and the transition state. So anything we do to stabilize the products will stabilize our transition state. Okay, and so as we increase the substitution of our alkyl halide, we would then increase the substitution of our corresponding alkene that we're making. Okay, so these three factors together all play a role in this rate relationship that we're seeing, in that as we increase the substitution of our alkyl halide, we increase the rate of the reaction. Okay, so the last major topic that we need to talk about for the E2 reaction is the stereochemistry. Okay, so like the SN2 reaction was stereospecific, the E2 reaction, being this concerted single-step mechanism, is also stereospecific. Okay, so let's write out the heading here. So we're going to talk about the stereochemistry of E2. Okay, and what we'll ultimately see is that it's a stereospecific reaction. Okay, so I just want to think about this for a second as it relates to or compares to other reactions we've seen. So the other stereospecific reaction we've seen are largely the addition of alkenes, where the EZ geometry of our alkene starting material influenced the product stereochem. So whether it was syn or anti-addition, we saw stereospecificity in that way. So how could a reaction where we're forming an alkene be stereospecific? Okay, so here what we're going to see is the absolute configuration of our alpha carbon and our beta carbon. So if our alpha carbon and our beta carbon are both chiral centers, the absolute configuration of those two chiral centers will determine the EZ geometry of our product. Okay, so we could have the potential for an E or a Z alkene, and in some cases, it will depend on the stereochemistry of the alpha and the beta carbons. Okay, so not every example of E2 will you have to think about this stereospecificity, but if your alpha carbon and your beta carbon are both chiral centers, you're going to have to go through the analysis we're about to talk about. Okay, so why is it that this reaction is stereospecific? Okay, so there's something I haven't told you about the mechanism, and that is that in the E2 elimination in our concerted single-step mechanism, there is a stereochemical requirement between the beta hydrogen and the leaving group. Okay, and that is that the beta hydrogen and the leaving group must be 180 degrees apart. They must be anti from one another. Okay, so let me write that out, and then we'll start to think about how this makes an impact on the stereochem of the product. Okay, so it's stereospecific because the beta hydrogen that we're removing and the leaving group that's being eliminated must be anti. The other way that we say this is coplanar. Okay, so anti and coplanar, not anti going against being coplanar. It's both of those things. They must be anti and coplanar. So anti meaning they're 180 degrees apart, which would also mean that they're coplanar, meaning they share a plane. Okay, so our leaving group and our beta hydrogen have to be in the anti-conformation. Okay, so I just said the word conformation, right? So hopefully what do you immediately jump to? Hopefully it's a Newman projection, right? We're gonna look at some Newman projections today to try to think about this requirement. Okay, and so the main reason why this is true is that in that the beta hydrogen and the leaving group must have this stereochemical relationship is an orbital requirement. Okay, so the orbital of the carbon hydrogen sigma bond, okay, to the carbon leaving group anti-bonding orbital, there is an orbital requirement there. So the electrons to transfer from the beta hydrogen that's being removed and then to flow them into the leaving group that's going to gain the lone pair, they must be in this stereochemical relationship 180 degrees apart. Okay, and so what we're going to see is that this requirement affects the EZ geometry of products. Okay, so it affects the EZ geometry of the alkene products. Okay, so it's stereospecific in that way. We could get an E versus a Z alkene depending on the absolute configuration of the alpha carbon and the beta carbon stereochemistry. Okay, so how are we going to do this? Well, we're going to look at a couple of examples. Okay, so we're going to look at these two examples. Okay, so remember I mentioned at the beginning of this that we really only have to go through this, what's going to seem like a complicated analysis if our alpha carbon and our beta carbon are both chiral centers. Okay, so let's write out our conditions. So here we have potassium ethoxide in ethanol. Okay, so strong base, strong nucleophile gives us this E2 reaction. Okay, so we can label our alpha and our beta positions. Okay, so notice how the two phenyl groups, so I'll abbreviate this up. So phenyl means benzene. Okay, so there is no beta hydrogens at this position. Okay, so we don't have to worry about the beta carbon on the other side because it's benzene, so there's no hydrogen at that position. Okay, so we're going to go to the beta carbon that I have labeled. So the hydrogen at that position needs to be 180 degrees from our leaving group. Okay, well, so this is what we need. We need this beta hydrogen and this leaving group to be 180 degrees. Currently, are they 180 degrees? Well, no, right? Because they're both going back into the board or back into your paper. Okay, and so you could do this analysis by either rotating around the carbon-carbon bond, as drawn in line angle, or you can convert to Newman projection and then do the rotation. I'm going to show it in both ways and show you how using either method you could predict the EZ geometry of our product. Okay. So let's go ahead and draw what the two potential products are so that you can see that there is a difference in terms of stereochem. Okay, so our two potential products are these. So that's one potential product. My other potential product is this one. Okay, so how are these two related? Well, we have the E isomer and the Z isomer. Okay, and we need to figure out which one is going to be the major product. Okay, so we have to go through this analysis of making the beta hydrogen anti to the leaving group. Okay, so we are going to convert this to a reactive conformation. So remember that conformational isomers were, two molecules that were related by rotation about a bond. So we're going to rotate this central carbon-carbon bond to make the beta hydrogen and the leaving group be 180 degrees. Okay, so we're going to rotate. Okay, and I'm going to actually rotate both the left-hand and the right-hand carbon because for me, it's easiest to put the beta hydrogen and the leaving group in plane. So let me draw that slightly more clear. Okay, so this is what I want to do. I want to rotate the left-hand carbon so that the hydrogen is straight up and the right-hand carbon so that the bromine is straight down. That will be a 180-degree relationship between this bond and that bond. One is up and one is down. Okay, so let's go ahead and do the rotation. So when I rotate around the left-hand carbon, my hydrogen is going to come to plane, my phenyl group is going to swing forward onto wedge, and then my methyl group is going to swing back to the dash. Okay, and then I can do the same thing on the right-hand carbon. So my bromine is going to swing down to where the phenyl is in plane, the phenyl is going to swing forward, okay, to a wedge, and then the hydrogen is going to swing back to a dash. So that was dash to plane, plane to wedge, wedge to dash. Okay, so I rotated both the left and the right-hand carbon, and now I have a 180-degree relationship between these bonds, right? So I have a 180-degree relationship here. So they are anti and coplanar. So the beta hydrogen and the leaving group are 180 degrees apart. So this is our reactive conformation. So it's the conformation under which the reaction proceeds. Okay, so we'll say the beta hydrogen and the leaving group are 180. Okay, so there are other ways that you could have drawn this reactive conformation. Like if you wanted to keep the hydrogen on a dash where it was, you could figure out where 180 degrees from that would be. That would be fine, and you could still go about the analysis. All right, so let's draw our mechanism and then think about how to predict the easy stereochem of the products. Okay, so our base was ethoxide. Okay, so we're going to have our ethoxide pick up our base, or our proton rather. We're going to donate those electrons to make the pi bond, and the leaving group is going to leave. Okay, so those bonds that I highlighted, that was the orbital requirement I was talking about. So for the electrons between the hydrogen and the carbon, for those electrons to flow into the pi bond and then into, into the bromine, those orbitals have to be aligned in this way, 180 degrees apart. Okay, so there's the mechanism. So how are we going to figure out, if the E or the Z product is preferred or the major product? Okay, so what we're going to do is look at the relationship of the phenyl groups. You could pick any carb, any substituent on the left and any substituent on the right. And for this example, let's look at the phenyl groups. Okay, so we're going to look at these two pHs. Okay, so both phenyl groups, both benzenes, are on the same face of that plane that cuts through the hydrogen, the beta hydrogen, and the leaving group, right? So they're both on wedges sticking out of the paper. Okay, so the two phenols are on the same side, which is in this case wedges. Therefore, they will end up on same side in alkene product. Okay, so look at our alkenes up above. Which one of them are the two phenyl groups on the same side? Right, the Z product. Okay, so in this case, we would get the Z isomer. Okay, so the Z isomer is our major product. Okay, so this is the product that's going to dominate in this reaction. Okay, so let's imagine, for a second that you were like, I didn't really like rotating that molecule, as it's drawn in line angle formula. Is there a way to do this by a Newman projection? Okay, so you could draw the original molecule, the starting material, as a Newman projection. Okay, and then rotate to make the beta hydrogen and the leaving group 180. I'm going to go ahead and just draw the Newman projection of our reactive conformation that we already determined, and then I'll show you how to analyze the Newman projection to come to that same conclusion that our Z isomer would be the major product. Okay, so we're basically going to take this perspective. We're going to look down that carbon-carbon bond, the beta carbon alpha carbon bond. So our front carbon will be the beta carbon. Our hydrogen is straight up. Okay, our one phenyl group's on the right, our methyl group's on the left, and then the back carbon, our bromine is 180 degrees. It's from our leaving, or our bromine is 180 degrees from our beta hydrogen, so it's straight down. Then we have one phenyl group on the right, and then our hydrogen on the left. Okay, so this is our reactive conformation as a Newman projection. So again, notice we have this 180-degree relationship between our beta hydrogen and our leaving group. One straight up, one straight down. We see them anti, remember that word anti that we used when we were talking about conformations. Okay, and they're coplanar, they share a plane. Okay, so how do I use this to come to the realization that both phenyl groups should be on the same side and I should get the Z alkene? Well, notice how they are on the same side. Okay, so both phenyl groups are on the same side. So they're on the same, can't really read that color, so let me write that in black. My pen's being funky. Okay, so both phenyl groups on same side. Okay, so that's the same analysis we made in the line angle formula perspective drawing. Okay, so if one of the phenols would have been on the left-hand side, they would have been opposite of each other, then I would have gotten the E alkene as the major product. Okay, so let's go ahead and do just that. Okay, so a few things to just keep in mind as we're working through this. So again, you only have to go through this analysis of both your alpha carbon and your beta carbon are chiral centers. And then the other thing to think about is what? Yeah, I forgot what I was going to say there, so sorry about that. Okay, so let's go ahead. Oh, I know what it was. So, how could it be that this is a stereospecific reaction, right? Like, so what do I have to change about the original starting material to get to the other isomer? Okay, so if I change both, if I invert both configurations at the alpha carbon and the beta carbon, I would get the same major product. It would be the Z alkene. Okay, so what we're going to see is that the alternate diastereomer. So in our example, we're going to invert one of the carbons. We're going to invert the alpha carbon and keep the beta carbon the same, and we'll see that it's the diastereomer that is going to give us the other EZ isomer, and we'll see the E product as the major product. Okay, so let's go ahead and go through that. Okay, so we're going to change the stereochemistry of one of our chiral centers. Okay, so our original, oops, make that more clear. So now I'm going to put the methyl group, I'm going to keep that on a wedge. But on the right-hand carbon, the carbon that bears the leaving group, I'm going to now put the bromine on a wedge rather than it being on a dash. So I've inverted this chiral center, right? So I inverted one chiral center, not both. So this is a diastereomer and under the same reaction conditions. So I have potassium ethoxide. How did I write that up there? Guess I didn't give them charges, so I'll be consistent here. So a potassium ethoxide in ethanol. Okay, so let's go ahead and rotate the carbon-carbon bond between our alpha and beta carbon. Okay, so again, we have alpha and beta. All right, so let's go ahead and do that rotation. So we're going to rotate to the reactive conformation. So the hydrogen I'm going to put straight up, and the bromine I'm going to put straight down. Nothing should have changed about your left-hand carbon when you do the rotation because we didn't invert the stereochem there. But at the right-hand carbon, now notice that my phenyl group is going to shift to the dash position. Okay, so this is the reactive conformation under which I'm going to do the mechanism. Okay, so now notice that our two phenyl groups are on opposite sides. One's on a wedge and one's on a dash. Okay, so two phenyl groups on opposite sides. So they're going to be on opposite sides in the alkene. So then if we wanted to draw our major product up here, it would be this one. Sorry, I just want to scroll this, make sure I draw this the same way. So our E product would be our major product. Okay, so let's look at this in the Newman projection to make sure that we can see it in that way as well. Okay, so the front carbon looks the same as it did in our first example. And then our back carbon, we still have our bromine straight down, but now our phenyl group's on the left-hand side. Okay, so now notice that the two phenyl groups are on opposite sides. Okay, so if you drew a line, that went through your leaving group and your beta hydrogen, you're going to ask, is relative to one group on the carbon, at the beta position and one group on the carbon at the alpha position, how are they related? So we chose the phenyl groups to do that. We see that they're on opposite sides. Okay, so they should end up on opposite sides in our major product, and we'll end up with the E alkene. Okay, so we can see now that we've changed something about the stereochemistry of our starting material, right? We were looking at two different diastereomers and their reaction under E2 conditions. And we saw that one of the diastereomers gave us a Z alkene, the other diastereomer gave us an E alkene. Okay, so we're seeing that the stereochemistry of our starting material influences the stereochemistry of our product. Remember that that's the difference or the definition of a stereospecific reaction. Okay, so we can see that this reaction then we could classify as stereospecific because of this easy dependence on the stereochem of the products. Okay, so the next thing I want to look at then is, along these same lines, what would this analysis look like for rings? Okay, so before we do that, I just want to reiterate one more time when you will have to do this analysis. So you will have to go through this conformational analysis of the beta hydrogen and the leaving group when you have chiral centers at both your alpha and beta position. Okay, then you need to do the rotation, make your beta hydrogen and your leaving group 180 degrees apart, and then figure out if the E or the Z alkene would be preferred. Okay, so let's look at the stereospecificity in cyclic systems. Okay, so stereochemistry in cyclic systems. Okay, so here's our first example. So there's our leaving group, and then we will put in a substituent at the beta position. So our typical E2 conditions would be strong base in our polar protic solvent. Okay, so first let's just label alpha and beta. So we have our alpha carbon, and then we have 2 beta carbons. Okay, this is not a bulky base. Sodium hydroxide is not a bulky base, so we would expect to get Zaitsev product if possible. So what we need to think about then is this beta hydrogen that I've labeled as, or this beta position I've labeled 1, is, that beta hydrogen, let's go ahead and draw it in here, is it able to adopt this 180-degree relationship to the leaving group at the alpha position? Okay, so what I need you to think about then is, well, how could I visualize that? So at a first approximation, you would just say, well, the leaving group's on a wedge and that beta hydrogen at, beta position 1 is on a dash. Those are trans, those are opposite, right? But in order to actually see the reactive conformation, we should draw a chair conformation. Okay, so let's draw the chair conformation to prove it to ourselves that that beta hydrogen needs to be trans to the leaving group in order to adopt that reactive conformation. Okay, so the only way for the leaving group and the beta hydrogen to be anti and coplanar is if they are A, trans to each other, and B, both in the axial position. Okay, so I'm going to put the bromine straight up. And this has nothing to do with which chair conformer is more stable and less stable. We are thinking about the reactive conformation. What conformation will we be able to undergo the E2 elimination? Okay, so here is our chair. Okay, so here was my alpha carbon, and here is my beta 1 carbon. Okay, so notice the bromine straight up, the hydrogen at the beta position that I'm going to remove is straight down. You could draw a Newman projection looking through that beta 1 alpha bond, and you would see hydrogen straight down, bromine straight up. That's an anti-relationship. Okay, so the only way that our leaving group and our beta hydrogen can adopt this reactive conformation is if they are trans to each other. Okay, so let's write that out. So only way for, oops, of course, I forgot to turn that off. Okay, so only way for the beta hydrogen and leaving group to be anti and coplanar is if trans and both axial. So one up, one down. And it doesn't matter which one's up and which one's down. In this case, dictated by the line angle stereochem, the bromine was up and the beta hydrogen was down. Okay, so then we could go ahead and fill in our mechanism here. So hydroxide was our base. Let's go ahead and draw that. So it's going to pick up that beta hydrogen. We're going to deliver those to form the pi bond, and then our leaving group's going to leave. All right, and so then in the products, we would see this is our major product. Okay, so the Zaitsev product. So in this case, we don't necessarily have an EZ issue to worry about, okay, because remember in rings smaller than 8 carbons or 8 atoms, we have to, the alkene has to be in that geometry. Okay, but I want to look at another example to highlight why this is important. Okay, so what if I took this beta hydrogen okay, and I inverted the stereochemistry at that position. What if the hydrogen was on a wedge? Okay, so this was our first example. Let's compare that directly to this next example. So I'm going to invert the stereochem at the beta hydrogen position. Okay, so I'm going to keep the bromine on a wedge, but now I'm going to put that methyl group on a dash. Same reaction conditions, KOH and water. Okay, so now my beta hydrogen that would give me my Zaitsev product is not able to adopt the anti-coplanar relationship because it is not trans to the leaving group. Okay, so I cannot remove that hydrogen. So where am I going to go? Okay, well, I could go to the beta 2 position, right? Because if I were to draw that beta 2, those two hydrogens at the beta 2 position, I could identify one of them that is in the right orientation, right? So I could go ahead and remove this beta hydrogen that is trans to the leaving group. So let's draw that in a chair and then think about predicting the products with stereochemistry. Okay, so remember that my leaving group has to be in the axial position. Yikes, okay. Maybe by the end of the semester, I will remember to turn that off when I use it. Okay, so the leaving group has to be in the axial position. That's the only way that it can be 180 degrees from the beta hydrogen that I'm going to remove. Okay, so I can fill in my beta 1 position. And so now my methyl group was at the position that I needed my beta hydrogen to be. So this is alpha and beta 1. So let's go ahead and draw in the hydrogens at the beta 2 position. Okay, so beta 2 is over here. Okay, so this is the hydrogen that I need to remove. This is the hydrogen that is 180 degrees from my leaving group. Okay, so if the beta hydrogen that would give me the Zaitsev product is not in the correct orientation, i.e. it cannot adopt this anti-coplanar relationship with the leaving group, I can go to the other beta position. So in this case, that was beta 2. Okay, so if we were to go ahead and do that reaction, we could draw the mechanism on here. Try to do that in red so that we have, so we can see that. Okay, so our base will take the proton, we'll give those electrons up and eliminate the leaving group. Okay, so what happened to the stereochemistry at our beta 1 position? Right, I didn't touch it, right? No chemistry happened at the beta 1 position. Okay, so in our products then, we would arrive at this. So that methyl group is going to stay on a dash, and that would be my major product. Okay, struggling apparently. All right, so there is our major product. And so notice this actually gives us another way to get to the Hofmann product. So let me zoom out so I can look at both of these. So in the first example, I got the Zaitsev product, okay, but when I inverted the stereochem at the beta 1 position, I couldn't remove that beta hydrogen then. So I had to go to the other side. So this actually gives us another way to arrive at the Hofmann product. And this isn't dependent on the base, like bulky base or not bulky base. This is dependent on the requirement of the beta hydrogen and the leaving group to be 180 degrees apart. Okay, so basically in ring systems, what you want to ensure is that the beta hydrogen that you're removing is trans to your leaving group. If it's trans, it will be able to adopt this reactive conformation and the anti-coplanar relationship. Okay, so at this point, we've basically covered everything we need to cover for the E2 reaction, and I realized that was a lot. So you should probably take a pause and get a drink of water and just try to absorb all of those things I just told you. Okay, so really the last thing that we need to do in this chapter then is we need to think about the comparison or the relationship between the SN2 and the E2 reaction. So I told you all the ins and outs of the E2 reaction, but under what circumstances would an E2 reaction occur? And under what circumstances would an SN2 reaction would occur? Okay, so I want you to remember that we already talked about SN1 versus SN2. And we learned that SN1 and E1 go together. So we already know how to figure out between the 1's mechanisms and the 2 mechanisms, right? So what we need to figure out is between SN2 and E2, what are the conditions that would favor SN2 and what are the conditions that would favor E2? Okay, so let's go ahead and talk about that. Let's see, how much time have I been talking? So we have about 5 minutes. All right, so we're going to talk about SN2 versus E2. Okay, and I think what I'm going to do is I'll give you the rules and I'll write out some examples, and then I'll leave the examples for you to work out, and then I'll work through them at the beginning of class on Wednesday as our last exercise in chapter 9, and then we'll start chapter 10. Okay, so the most important factor for SN2 versus E2 is going to be the electrophile again. just like it was between SN2 and SN1. Okay, so the electrophile again is going to be our most important factor. Okay, so methyl halide, primary halide, secondary halide, tertiary halide. So methyl, primary, secondary, tertiary. So we already touched on this a little bit in class earlier today, but remember that the methyl and primary halides are going to favor SN2. Tertiary is going to favor E2. Okay, so SN2 cannot operate on a tertiary halide. And then what about secondary? So secondary could be either SN2 or E2. So either SN2 or E2, and it will depend on the other conditions. So it depends on the nucleophile, the base, etc. Okay, so if we have a methyl or a primary alkyl halide, we just want to make sure we have a strong nucleophile. Whether or not it's a strong base, it'll undergo SN2. For E2, we require a strong base, as we were talking about. So as long as we have a strong base present with a tertiary halide, it'll go undergo E2. Well, what about if I have a secondary halide? How do I know if it's SN2 or E2? Okay, so that's where we're going to move to the nucleophile or base. Okay, so nucleophile slash base. Okay, so if it is a strong nucleophile, it's going to favor SN2. Okay, if it is a strong base, it'll favor E2. Okay, so really we're using this criteria if we have a secondary halide. Okay, so how am I going to know, since usually nucleophilicity tracks with basicity, how am I going to know when a nucleophile is only a strong nucleophile, not also a strong base? Okay, so our book gives this criteria. So they say that the pKa of the conjugate acid is greater than 11. Okay, so what I'm going to do is I'm going to go grab our table, our nucleophile table, and I'm going to paste it into our notes, and then we can try to identify some of those nucleophiles slash bases that have pK of a conjugate acid greater than 11. Okay, so give me just 1 second to do that. Okay, so I went and got that nucleophile table, 9.7, that was in our notes from sometime last week. And I want to go ahead and just look at this chart and think about which one of these nucleophiles slash bases have a conjugate acid with a pK greater than 11. So basically what we're saying, if we have reached this threshold in basicity, that base then will promote an E2 reaction, and the E2 rate will be faster than the SN2 rate. Okay, so let's think about, first the OH-based nucleophiles and bases. Okay, so remember that water and alcohols have a pKa roughly 15. That's greater than 11. So that means the conjugate base of, water and the alcohols would be considered strong base for this purposes. So here we would have alkoxide, methoxide, hydroxide. Those would all be strong base, strong nucleophiles. The other one would be NH2 minus, amide, like NaNH2. So remember, ammonia has a pK in the 30s. And so we would expect to have, that's greater than 11. So that base NH2 minus would be strong enough to promote an E2 reaction. And then the last one is acetylide. Okay, so we had briefly mentioned that acetylide anions as nucleophiles generally prefer to react with methyl and primary halides, but we never really knew why, but we're now learning why. So if we were to use an acetylide anion as a nucleophile with a secondary halide, we would have a considerable amount of E2 in competition with our SN2. Okay, and so there is ways to use solvents to kind of tip the scales. So we know that aprotic solvents favor the SN2 reaction, and so it could be that you could use a polar protic solvent to then favor E2, and an aprotic solvent to favor SN2, but ultimately the strength of the base is going to be more important than the solvent effects. Okay, so then the last thing that I want to mention is just something you might see with some of the eliminations. So the third clue you could use is the temperature. Okay, so the temperature. So what the deal is that usually elimination reactions are favored in the presence of heat. Okay, so heat, so we can abbreviate that as delta, leads to elimination. And the reason why is because of an entropic term. Okay, and so remember that we had this Gibbs energy equation that's that ended in T delta S, and so the entropy was dependent on the temperature. So as we increase the temperature, that entropic term becomes more important. Okay, and so heat can help us, that's just a clue. So oftentimes E2 eliminations will have heat, and so that's just like an additional thing that you could look for when you're trying to decide between SN2 and E2. Okay, so the last thing that I want to put in our notes then is this table from our textbook, which basically has summarized all the rules between SN2, E2, SN1, E1. Okay, so we're basically at the point in class where we're able to play our really fun game, and that is going to be, so SN1, E1, SN2, or E2. Okay, and so you can look through this table, but it basically breaks down for methyl primary, secondary, and tertiary when SN2 would, or SN2 E2 or SN1 E1 would occur. So one thing that I want to point out is, under which cases could a primary alkyl halide undergo E2, because that's not necessarily one we saw. But notice if you use a bulky base, we can get E2 with a primary. Otherwise, primary halides typically undergo SN2. And then you can read through the rest of this, but it basically summarizes, the table we have in our notes on this page, and then the table we have in our notes that's comparing SN1 to SN2. Okay, so let me write out a few examples here. And again, I will start in class on Wednesday with these examples, working through them, but I want to give them to you so that you can practice going through these, and then we'll work on them together on Wednesday. Okay, so here are these last examples to work on. Okay, so again, what you want to do is look at the identity of the alkyl halide and then go to the identity of the base and nucleophile to think about what the reaction will proceed. All right, and one last one if you're still with me. I guess I don't need stereochem there. Okay, and if you happen to still be here, I wanted to mention one other thing, and I'll try to say this in class on Wednesday as well. But that is, you might have noticed on the last page when I clicked to that on accident that I had something there. So if you wanted a more interactive way to practice some of these skills related to SN1, SN2, E1, E2, there's this game produced by a man named Neil Garg, who is a professor in chemistry at UCLA. But he made this game called Backside Attack, which you can download and play. It's kind of funny. So I just wanted to let you know that that was a thing. Okay, so just to reiterate, on Wednesday in class, we will go ahead and go through these examples. I will, talk about the electrophile, the base, and we'll go through and decide SN1, E1, SN2, or E2, and then we can predict the products. All right, so I'll see you guys all on Wednesday.